Okay, so we're back on the moon. In case you didn't catch parts 1, 2, or 3, the whole questions, I'm answering the same question multiple times. So here I have the moon. This is my ancient model of the moon with no back. And I have an object that starts 3 radiuses away and it falls down to 2 radiuses away, and we want to find out how fast it's going. So the first time I did this, I did the momentum principle, and I assumed an average constant force, which was wrong. And then I did the momentum principle, and I found a numerical calculation for it so that I could break it into pieces, and that was much better. And then I did the work energy principle. Now, for the previous work energy principle, I assumed that the force was constant, and I just broke it into small distance steps, and I calculated the total change in velocity that way. So here are my 3 values. They're all around 1,000 meters per second. We're going to do it again. And if you're tired of this, I don't know what to tell you, because I like it. Same problem. Okay, so let's do the same thing. We're going to let the object fall from 3r to 2r in the y direction. I'm using the y direction just because I have no idea why. And I have a changing force. So I still want to say the system is the ball. It's whatever you want to call it. The object, the mass is falling. It's 100 kilogram mass object. Okay, so now I want to say this. The work is going to be equal to F dot dr. F, which I can calculate, dot delta r, but that's not constant, so I actually have to use a different definition of work. I need to calculate the work along all these little steps, and then I need to let the step size go to 0. I'm going to take the limit as the step size goes to 0, and I'm adding up all the steps. And if you've taken calculus, you should say, aha! That's an integration, and it is. So really, work is defined as the integral from, I'll call this R1 to R2. This is 1, and this is 2. I'm thinking in my head, because I know I made a mistake on this, and I always make a mistake. I'm not going to make it this time. Okay. So it's going to be F dot dr. Okay. And then I have an integral. I can integrate and find the work. And that's still going to be equal to the change in kinetic energy. Okay, so up here, the velocity is 0. Down here, I want to find V2 equals V1 equals 0. Okay, so let's do F dot dr. So F is going to be the vector negative g, mass of the moon, mass of the object, over, this is going to be y, I'm in the y direction, y squared, and this is going to be 0, negative 1, 0. That's a vector, right? Because I already put the negatives in there. So it's in the negative y direction. dr is going to be the vector 0, dy, 0. And I'm going to show you at the end the mistake I made here. And here's the mistake. So I'll tell you right now. And then I'll play a little clip where I try to figure it out, because it's fun, with a friend, because we make mistakes too. Okay. So dy is not negative even though I'm moving in the negative direction, because I'm going from position 1 to 2. I'm defining the direction by my integration limits. Okay, so that's important, because I do want there to be positive work done on the object, but I'm going to get that. Okay, so if I take F dot dr, I get negative. Feel like I make a mistake. No, I didn't. Negative g m of the moon m over y squared dy. That's my work in the tiny little step. Okay, and it's a scalar. Now I can integrate that. So now I can say the work is the integral from r1 to r2, negative g, mass of the moon, mass of the object over y squared dy. I can integrate that because it's just a power rule. Negative g m moon m of the object is just a constant. So that comes out. Then I get 1 over y, dy over y squared. The integral of that's going to be negative of that, dy over y. I mean, 1 over y. So I get a negative sign, because this is y to the negative 2. So I get g m mass of the moon mass over y from r1 to r2. Okay. just feel like I made a mistake. I haven't, made this mistake many times. But I know if you know you make a mistake, it's not such a bad mistake, right? Okay. So let's do this. So now if I evaluate the limits in integration, mass of the moon. This is the 4th video I've made today. Okay, so I'm getting kind of messed up. M times the final y, which is going to be 1 over 2r minus 1 over 3r. Okay, and I want the work to be positive, and this is positive work. I did it because this is a bigger number. This fraction is bigger than that one, so I do get a positive value. Okay, but that's going to be equal to my change in kinetic energy. So it's 0, the final kinetic energy, 1/2 mv2 squared minus 0. So now I can solve for v2. So I get v2 equals the square root. So that mass cancels. I get 2g mass of the moon times 1 over 2r minus 1 over 3r. I think. Okay. So let's put that in my Python calculator. Okay. I'll just use this real quickly. You can put this in your calculator if you want, but let's see. Let's copy this and let's delete all this stuff. So I have the mass of the object cancel, as you can see that here. I have g, I have mass of the moon, so I'm going to get v2 equals the square root of 2 times g times mass of the moon times 1 divided by 2 times r minus 1 divided by 3 times r. I feel like I have a parentheses problem, but no, I think I'm okay. Print v2. I get 970. So let's erase this. 970 meters per second. Work, energy, 2. Okay, so this is good. I get essentially the same thing as when I did it numerically, which makes sense. I get a little bit different answer than my numerical, but I think that's just because of the time step, and I think I could fix that. Okay, so let me show you. I think I'm actually thinking ahead, so it might not actually be there. I'm pretty sure I have a clip of me and my colleague, Dr. David Norwood, and I had a problem like this where I got the minus sign wrong, and I did it a bunch of times, and he helped me figure it out. So we kind of worked it through together. So I think it's important to include that at the end too, just so you can see that we're people too. Okay, but that's solution number 4, and we're gonna do a couple more. Okay, so here I have an object going from point 1 to the surface of this moon, or a space station.
Fall.
It could, yeah, fall. Okay. And so I want to calculate the work done by gravity.
Okay.
That seems good, right?
Yeah, that's what I would do.
Okay, so I called this the x direction. So this is my F force.
Yep.
And it has a vector and unit vector -1, 0, 0.
Got it.
You okay with that?
Yep.
My dr vector is -dx 0, 0.
This is the 2 minuses and what happens.
Yes, it's the 2.
Yeah, I do that, and every time I have to figure out what I did.
Yeah, and I don't know why I keep making. Okay, maybe we can figure it out. We got 2. You're minus, I'm minus. We figured it out together.
And you're gonna what's the word?
Blog?
You're gonna blog it.
No, I'm not gonna blog it.
And that way we won't have to do this again.
Okay, I will.
We won't have to do
on my
this
personal page. On my personal page. So you're okay with that?
Yep.
You're okay with that?
Yep.
You're okay with
and
D?
F.dr has no point. F.dr is positive.
That's right, which makes sense, right?
Because it's going to pick up speed.
Which it should.
Yep.
And a dw. But then when I do the integral from x1 to x2 of this, I get a negative, and then I go from 2r to r. I just pick values. Then I get.
This you're already wrong here.
Well, if I integrate this, don't I get a negative?
Yeah, but something's got to be wrong. Well, no. Okay. Hang on. But then you're going from a big number to a small number. You're dividing by.
Yeah, but I go from
big.
initial to final, right?
Yeah, yeah. You're right, but you go from a big number to a small number, which means minus plus. Yeah, this number is bigger, so that's smaller, so the whole thing's negative.
The only thing.
Yeah. This is where I arrive.
And then you go, just make that negative.
Okay. I swear I have played that game, as we all have. However, I have actually also fixed the problem.
But you don't know what it was.
But I don't remember how I fixed it.
See? This is why I'm recording it.
Oh, so now everybody knows that.
So we will know how we fix the problem.
I just actually, I solved this, I solved F equals ma though.
So here's what I was thinking. I thought about this during the seminar, because you know.
Dx is negative.
So here's I'm going.
The reason we were happy here. Hang on. The reason we were happy here is this should be positive, but dx is negative.
But I put it right here.
Oh, that's no. You put it here, and then you put it here. I think you put it in twice.
So you're saying that once I set dx, I can't say it's going that way. I've already said it's going that way with the limits of integration.
Exactly right.
Okay, so the best thing to do is say dr is that.
dr is dx, and here dx is positive. All is
I
well.
set the direction by the
Now-
limits of integration.
And now you say you're going closer.
I set the limits that the limits of integration tell me the direction, not this. And
And-
this
and
you
now
know who
that-
this video is for?
And now that we figured this out, I now remember that's how I fixed this problem before.
You know who this video is for?
You.
Future Dave.
Future Dave. And future Red.
Well, thank you very much.